It's going to be challenge assessment 3 by me, Hunter Casa. Going to solve a problem from the full heat conduction equation. I'm going to identify and express the boundary conditions, go over the mathematical equation for the temperature distribution, graphically represent the temperature distribution, adjust 3 parameters, and analyze the effects on the problem. And I'm going to go over how to improve this scenario. So this is the problem. It's going to be a resistance wire of radius 0.6 running through water at 100 degrees Celsius. The thermal conductivity is K, which is 15.2. Heat generated is 16.4 watts per centimeter cubed. And the heat transfer coefficient is at 32,000 watts per meters squared Kelvin, H. So from the very first full heat conduction equation, this is going to be steady state, so we're going to cancel out this left side. Q triple prime is in the problem. Then we're going to pull out K because it's constant. Then we're going to have this gradient over here, which is going to turn into this equation right here. As we simplify a little bit. And then we're going to take the first integral of that. We're going to get from this equation right here, which is just this simplified a little bit more. We're going to get this equation. We're going to have C1. We're going to take the second derivative of this whole equation right here. We're going to get T with respect to R equals all of this. And we're going to have two constants that we're going to have to solve using the boundary conditions. So there's no initial conditions that we need because no time component. The first boundary condition is going to be convection, and the second is going to be symmetry. The second boundary condition is symmetry, as I said. This is going to help us solve for C1 equal to 0. And this dt dr, we're going to use it from after the first integral of the heat conduction equation. We're going to plug in at 0, and we're going to get this, which is C1 equals to 0. This helps simplify the problem. And then boundary condition 1 is going to be the convection equation, which is listed right here. And I'm going to have negative H in this situation with how I mapped it out. Then we're going to use this equation right here, which is the T with respect to R. We're going to plug it in here. We use it after the first integral right here, equation that I talked about earlier. We're going to plug it over here in negative K. Now once we simplify it a little bit, this is what we're going to get. And we're going to have to solve for C2, and then C2 I got to be this whole equation right here. Now I'm going to have to plug that in to the original T with respect to R to plug in the C2. After simplifying that equation a little bit, this is we got Q triple prime times all of this over 4 over K times all of this plus T infinity. So I'm going to use that equation. I'm going to plug into, or I used that equation and I plugged in, graphically represent this temperature distribution from 0 to 0.006 meters, which was the total radius of the pipe. These are the numbers that I got. I'm going to go over to how to analyze the effects on the problem while changing the 3 different parameters. First one was going to be Q triple prime. These are the 5 different numbers that I used with respect to it. And this is just all the data that I got. So as you can see here, increasing the Q triple prime is going to be bad. We are going to want to decrease it, as the 15.2 times 10 to the 6th, I think it was. It's going to be the best situation down here. This is our original problem, so if we decrease it, we're going to be getting a better system. Then changing the H, I used another 5 different. And these are all the data values that are associated with that. Then we're going to see that increasing the H actually makes it a better system, which is the green down here. And then this is the original orange right here along this path. These are all just being shifted so far. This next one, when I change the K, with these 5 different problems, you're going to see that there's a slope change. So they all merge down to the same spot at the end, but the larger K values is going to be having less of a slope compared to the smaller K values. So we're going to want to, in this problem, increase the K to have at least less heat loss. So going back over how to improve the scenario, I'm going to be decreasing the amount of heat having to be generated and the total heat lost. I'm going to decrease the Q triple prime and increase the H and the K. decay will really help to decrease the heat loss because it's going to be shrinking down the slope. There's going to be less heat loss, and we're not going to have to regenerate heat to as high of a spot as it was before. So this is going to be a perfect system where I use the K of 17, the H of 4000, and the Q triple prime of 15.2 ... And as you can see, there's a slight slope decrease, and a total difference in the temperatures is going to be about 8 instead of being 10 as it is right here. And it's also going to be starting lower and finishing lower, so we're going to have to generate less heat. We're not going to have to get up to this 398, we're only getting up to this 392. And then we're losing only 8 degrees of Kelvin instead of the 10 in the system. Thank you.